Boom. Hello and welcome back to Calculus 3, section 12.3, finally, right? On limits and continuity. So far we defined the function of several variables. We said that the function, first we know that y equals f of x, which means input x, f acts on it, y goes out. Then we upgraded to z equals f of x y last class, which is two values come into the box and z value comes out. So your previous experience all the way through Calculus 2 was one-dimensional input, one-dimensional output. Now we are at the place where we're going to say that your output, let's call the output y, is going to be a function of several variables. And I'm going to actually put many values here, right? And then just draw the diagram where multiple inputs are coming in, and each one of these is some kind of a function. So we can have as many variables as we want, and then we are having a one-dimensional output, which is called the range. Now we are focusing on the second line, but we are going to see some instances and cases when we have four variables working in the fourth-dimensional space. As I mentioned earlier, if you're designing, let's say, a cell phone, you want to know the temperature distribution because the components inside, especially processor, have to cool. And if the temperature is well distributed, then the cooling is better. So you want to know function for temperature distribution, for instance, and design cases and heat sinks and heat tunnels and all the other things that are part of the technology that would actually make cell phone a viable device to use. So yes, we are going to use some of the 4D concept as well. Now, going back to our definition of a function, so z was equal to the function of x and the y, and we know that our input is now two-dimensional, so x and the y, and the whole thing over here is the domain. We practiced many problems last time to figure out how to find the domain. And now we'll have the one-dimensional z, which is the range. So that's preliminary, what we need for this lecture. Another thing that we need for this lecture is the basic knowledge of limit and the definition of the limit and what it means from Calculus 1, because we are just going to add one more variable now. We're not changing pretty much anything. So if we go back to Calculus 1, we want to have the basic idea of the limit. And generally what I say to my Calculus 1 students is that the limit is the fancy way to find the y value, right? So instead of word fancy, you can use advanced or different or whatever. But I like the word fancy way because it is still giving you the y value just like pre-calculus does, but it does it in a really cool way, and it can also give you a solution even when the point is not present, which is why I fancy the word fancy. I know it's too much, but that's okay. It's that kind of a day, so there you go. So for the limit, we are technically computing the y value of the expression. So if I am to say that the limit of x squared as x goes to 3 is 9, well, that's what it is. It's correct, right? And actually the y is the answer when you plug in 3 into this function. So if I am to compute now f of 3, I would say 3 squared, it's 9. So you have a calculus way to compute this and the pre-calculus way to compute this. Now, the difference is between these two calculations is conceptually difference is big, it's large. because these two concepts compute the same problem in a very different way. So I'm going to draw a graph of x squared, which is just a parabola. And I'm going to say, let this be that number 3. Which produces the output over here of 9. Now, we have the same picture on the other side, and I'm going to do the whole thing. 5, 3, 9. Nice. The way we did this in pre-calculus is we locate where 3 is on x-axis, then we draw the line perpendicular to the x-axis, and wherever it cuts through the function, bounce it back into the y-axis, and that will be the answer. So for the properly drawn graph for x squared, as you go up from 3, it will hit the function, bounce off, and that's the calculation at that point. Limits do not compute that way. Limits compute everywhere else except at 3. So for limits, what I call this Romeo and Juliet approach, so we approach 3 from the left, meaning your x values are marching 2.9, 2.99, 2.999, 2.9999. So it keeps getting closer and closer, which means that the y values are climbing up the line and they're climbing up y-axis. And now the Romeo approach from the other side, right, blue for the boys. We go to the left, right, which pushes down the line, which pushes down the y-axis, and you see that they meet at 9. So the squeeze, right, that we have on x makes all of the y values squeeze into 9. Now that's what is the meaning of the approaches 3. We do not compute at 3. We look at the trend of all y answers as you are picking all x values that so that they are approaching 3. That's the concept of the limit. And now we need to take that concept and put it in a 3D environment with a lot more issues and problems, obviously. But please observe the red arrow and the blue arrow. You are only able to approach 3 from the left, which is red, and from the right, which is blue. And there is that huge theorem in Calculus 1 which said that the left approach and right approach, if those two are the same number, then your overall limit is that number. And you can actually see it there from the graph that both red and blue are squeezing into 3, and then the red and blue on y-axis are both squeezing into 9. So the left calculation, which is red one, gives you 9, and the right calculation, the blue one, is also giving you 9. Therefore, the answer is 9. Now, again, I will have to stress that we never computed at 3. We computed at all infinity of the values around 3. We never computed at 3. Now, that is very important because it allows us to use this concept to calculate the limit, y value, even if the value does not exist, if it's not defined. So if you have a function with a hole in it of some kind, you are still able to compute the limit of that place, right, which would be f of a. Now, you can't compute. You see, if you go and you say f of a, you have to say it does not exist. Right? So f of a does not exist because a is not defined. You know what the pre-calculus says. You have to go and hit the function, and then you bounce off of the function into y. Well, over here, when a starts going up, right, it's going to pass through the open circle and never bounce off to give you the y value. But the limit of f of x as x approaches a in this case does exist, and it's L. And we can find it because all of the values for the red approach, they all exist and they're well defined. So I can figure out the pattern from observing all of the values for the red and blue, and looking at those y values, they're going to scream that the answer is, let's say, 7, right? Because from the left and from the right, they both approach 7. So this is the idea of the limit. Your job is to compute just the y value. That's what the limit does. Gives you the y value back, right? But it does it in a different way, what I call the fancy way, right? It computes at infinitely many points to the left and infinitely many points to the right without actually computing at the point, which allows us to have a situation over here. Put backpack.
Oh my God.
Any food inside? Anyway, so we can deal with the pre-calculus situations where everything is perfectly defined, but then we can also use pre-calculus to deal with that, right? There's no need for a sledgehammer because pre-calculus works just fine. However, for all awkward and weird situations with circles where the point is not defined, with the vertical asymptotes, or anything weird happening, clearly we want to bring in the big guns, right? So limit is there. Now, another and the last review point that you really need for this lecture is the notion of that left approach, right approach, which is the huge theorem, the biggest theorem for limits, which says that the overall limit exists only if the left limit is equal to the right limit. So the theorem says this: if limit x approaches a minus, which means from the left, of f of x is the same as the limit as x approaches a plus from the right is equal to L, then the overall limit x goes to a of f of x is L. It goes the other way, right? So I should say if and only if, but so now second sentence over here, otherwise limit does not exist. This is a big statement. So let's take a look at a case. So I'm going to put a function with a jump discontinuity. Is this a function? Yes, it is, right? It passes vertical line test everywhere, so we're good there. Now, if you observe what's happening at A, right, you should come to conclusion that limit does not exist. As you approach from the left, you will be approaching the open circle point, which would be giving you this as the answer. And if you approach on the blue side, you would be approaching this as the answer. And clearly, blue point and the red point are not at the same location, so it violates the theorem we just have, and this is how we know that the limit does not exist. You are going to need this for this section. So limit f of x as x goes to a does not exist. Bueno? Nice. Very good. So now, you might, before I do this, you might or you might not remember that we have a precise definition of a limit with epsilon and delta, which was coined by mathematician Weierstrass in 1850s somewhere, which says that we write that the limit of x goes to a of f of x is equal to L if for every epsilon larger than 0 there exists delta larger than 0 such that the difference between f of x and L is smaller than epsilon whenever 0 less than a minus x minus a less than delta. There we go. So this statement is the official statement as a definition of the limit, and we are going to use the same thing now to go 3D, also known as R3, right? So what am I going to do now? Now I'm going to have, instead of f of x, I'm going to have f of x y. So my definition for the limit of two variables changes, and you can generalize it to more, obviously. So the function f has the limit L as p approaches p0. So here we go. So now the notation is limit x, y goes to a, b of f of x, f of x, y is equal to L if for every epsilon larger than 0 there exists delta larger than 0 such that f of x, y minus L less than epsilon whenever and now we're going to use the distance over here, so 0 less than, and we have the distance formula, which is x minus a squared. It's not gonna fit. So we have the x minus a no coffin squared plus y minus b squared is less than delta. Now, if you carefully observe this over here, I hope that if you see that you can see it in your mind's eye. If you replace the less than symbol with the equal sign and you square both sides, you are getting equation of the circle, which is centered at AB. Remember, you are approaching AB. So now, what's new in Calculus 3 for the limits that it's so different from Calc 1? Well, domain is different. Your domain used to be x-axis only, now it's xy plane. And that brings a lot of headache. Because on your old domain, to approach A, you can just come from left or from the right and you're done. Right? In our new setting, to approach point over here, you can spiral in elliptical fashion. See that? That has to work, as well as the linear approach, as well as the trig approach you might have. We went from having approach from the left and approach from the right to having approach from infinitely many directions in infinitely many ways. And that's an issue. It's not easy to compute anymore, right? But at least what is still easy to compute is when there is no limit, right? So yeah, we're going to do the same thing with theorems and say that, you know, polynomial-like creatures are all right, the limit. So yeah, we'll have some of those where you can just plug in and be done, right? But anytime when you get 0 in denominator, those are tough ones. Because we know well from Calc 1 that certain problems with the limit, when you have 0 in denominator, are finite in their limit. Right? We can come up with those easily. Just use, let's say, x squared minus 16 divided by x squared plus 4. X plus 4 in the denominator. That one has a finite limit. Right? It might look like it has infinity, but no. Right? One of the terms cancels, and the other one that survives is the one that gives you the answer. And the answer is a fraction in that case. So you cannot bank on the fact that if the 0 is in the denominator, you have limit does not exist. So we'll see which way we prove that the limit does not exist. So what should I do here? Well, first off, we have to deal a little bit with this issue of two inputs, right? You have x and y, and they both contribute, right? So theorem 12.1, limits of constant and linear functions. Well, limit of a constant in a constant, so that's simple, right? So limit of c is c, and this xy can go to whatever the hell it wants to go. It will, limit of c will always be c. Now, for constant functions, so we have limit of x and then a limit of y. So xy goes to ab. Note that there is no mention of y over here at all. Therefore, I have nowhere to plug this b. So the answer over here is just a. And then in the second one is just b. Because there's nowhere to plug in x. You know, x goes to a. But there are no x's there, it's just y. And y goes to b, so answer is b. Now, they did the proof for this, obviously, and all that stuff. Now, all of the properties of limits are the same, like in Calc 1. So all of the properties, all of the limit properties are the same. You have much more freedom than the derivatives, right? Because you can do sum, difference, and also multiplication you can do individually, division you can do individually, but for derivatives and integrals you have to use other techniques. Constant multiple, and then the power and the fractional power. So everything that we learned in Calculus 1, all of the properties are the same for Calc 3. No difference in any of them. And now we get to this issue of, boundary points and situations when limit does not exist. So please recall that in our previous lecture, we were looking for domains, and every time we figure out the domain, we draw the domain, and we know that the set of points that we want to use is inside the domain, and set of points that we either don't want to use or can't use are outside. Now, there is this edge, a separation between the realm of the domain and the other realm that contains the rest of the stuff that is not in the domain. And a point of interest sometimes can be on that edge. So, for this drawing, let's say, a point is right there, right? Now, the great thing about this is that I can still approach this from infinitely many angles and functions and whatever, as long as I'm on my shaded path. And again, if all calculations are pointing towards that point, just like, remember, my Calculus 1 example pointed towards 9, right? So if all paths that you check point towards this, and there are infinitely many of those paths, if all of them point to that point, well, if it walks like a duck and it quacks like a duck, it's pain. I know you love him so much. Oh, actually, yeah. A delayed reaction, I'm sorry. It's clearly a duck. I'm sorry?
You did that on purpose, right?
Did what on purpose?
The duck today.
Yes, because you're here. Yeah.
Well, okay.
Weren't you standing up for geese?
These aren't ducks.
I know, but it's close enough. It's still edible. Anyway,
Good.
process is the same. Plum cooking, there you go. One thing you can avoid in that point. No, no.
Carrie. Okay.
All right. Now, I'm going to use the image you see over here to define the interior point, right? And the boundary point. So interior point, right? So you're now thinking of the point that is inside the shaded region, which is your domain, like that blue point on x-axis, right? That is in the shaded region. That will be interior point. Interior point in mathematics is defined this way. You are able to draw a circle around it of any arbitrary radius. Doesn't matter how small or how big, you are just need to be able to draw a full circle of whatever radius you can fit around. If you are able to do that, the point you are talking about, the point you're observing is interior point, right? Now, the boundary point is the one that sits on the division line, right? Dividing line between the realm you want and the realm you don't want. Boundary point, when you draw a circle of arbitrary radius, in that circle, some points are in and some points are out. So, I'm going to draw those two circles I'm talking about, and you can see that on the boundary point, the one on the line, right, in the graph, on the boundary point, you have some of the points right there, right, are outside, and these guys are in. So if you have some in and some out, right. A student once asked me, well, can't we just draw a bigger circle? No, you can't. All right?
Good question.
Yeah.
Which one is which? The boundary.
Boundary is on the boundary and interior point is inside. Let's go back to our lecture. So now we know interior and exterior points. Now this will be used further in the course. And now we want to deal with problems that are having the limit on the boundary point. So, if you know the domain of the function, because you looked at it and you practiced the previous section, so if you know the domain of the function, and you see that the point that you are approaching is on the boundary, most likely that problem is solved by using algebra. Algebraic manipulation of some kind. So either you are going to factor or you are going to rationalize. You know, it's something that algebra realm can help you with. So let's take a look at an example of such a thing. So boundary point problem. I'll call it boundary limit. So you have that the limit xy approaches 4, 1, and the function is given as xy minus 4y squared divided by root x minus 2 root y. clearly the first impulse is to plug the value in and hopefully get the answer. If you're not able to do that, then we have issues. It's a y squared, yes.
So what's going on to the left of it? I think it's 4.
This over here is 4.
Haha. Yeah. Now it's 4.
Is that XY versus 4
XY approaches 4. What is with you and 4s?
What's with you and 4? Okay, that's a question.
Oh yeah, there's now that thing, right? If I'm the only common denominator in all the questions, then it's me. It's never me. All right. So let's go. What you need to have as a skill from Calculus 1 is that any limit you see, since they compute y values, natural response is just to plug numbers and hopefully compute the value. If that fails, then you have to think about other methods, right? So let's start with try to plug a number. Now, I always start plugging a number in denominator first, because if that works out to be 0, then the method is doomed, right? So I will plug in x is equal to 4, right? So square root of 4 is 2, minus 2. Well, I got 0 in denominator. So this means that we cannot solve the problem by plugging in values directly into the problem, right? And we know this is a boundary limit problem. Therefore, we should massage this with algebra to get different form that would hopefully solve the problem. Manipulate. We don't know how to take derivatives yet.
Oh.
What happened? It's not, no. See, implicit differentiation is when y is a function of x. In this case, x and y are completely, they're both independent variables. They're equal in that respect, right? And z is dependent on both of them. So implicit differentiation would not. It's an excellent try. It did fail, but it's excellent try. It's excellent try. It's excellent. No, I'm very happy that you actually remember implicit differentiation. How many of you remember implicit differentiation? If I'm to give a quiz now for, let's say, 30 points towards final, it replaces final exam. How many of you would be able to do implicit differentiation right now? Oh, look at that. Well, I know, right?
Would you rather do like calculus or implicit differentiation?
By the way, 8 people raised their hands. Anyway, we needed this. Oh, by the way, did anyone? Juan, you're winning for so far.
I'm winning?
Yeah.
Ooh.
But like when we do eventually learn how to do derivatives, does the calculus apply or no?
No.
People voting to try to vote for one.
One more.
Yeah, there's no other ticket.
Anyway, relax. No. No, not. You're not. I'm serious. Are you on the group chat? No. Exactly. It's the truth. All right. Let's solve the problem. So, which way should I attack this problem? Well, algebra. Factor, or rationalize. But I like to factor. It's better. All right. So, let's see anyone with sunglasses. No one has sunglasses. Yeah. Anyway, so let's go. Limit x. We're focusing on a problem.
No, you're not.
Factor out y, and we have x minus 4y divided by root x minus 2 root y. I factor out y in the numerator.
But I thought when
And now we are going to factor the numerator further. Anything can be factored. It doesn't have to be perfect square. It doesn't have to be. So I'm going to say y, and then root x minus 2 root y times root x plus 2 root y. And then we have root x minus 2 root y in denominator. They drop. I know. Who would say that you can factor x minus 2? Right? This is what I did. I factored out x minus 2.
Where's the x minus 4y go?
Into these two. I factored it by writing, let's say, root x minus root 2 times root x plus root 2. We can do that. You have never done it before, maybe, but it's doable.
Wouldn't that be x minus 2? Not minus 4?
Where? Well, this is a completely different problem, but I'm just explaining the concept. Maybe I should use 3's here just to make sure that has nothing to do with the problem above. You can factor anything, any difference. It doesn't have to be x squared minus 100. Yes, you just add i's because it will be complex domain.
You want to use imaginary numbers?
No, I'm sorry for your disappointment. Right? That's... Oh, you had enough?
Yeah.
All right. So now, once I've done that factoring, these guys cancel, and now I have...
Oh, I see what you did now. It's taking like a while. Yeah. But
Okay, but no, as long as you see it, that's great. So now we have y. Oh, no more denominator. So I just have y of root x plus 2 root y, and we can see we can just plug numbers in now. So y is equal to 1, and root of 4 plus 2 times root of 1. So this is 4. So this was an important limit because you see that we have 0 in denominator. And if you claimed, because 0 in denominator, that limit is undefined, well, clearly you would be wrong, right? Some of the limits with 0 in denominator are undefined. Others have one of the infinities as answers, and others have finite value. So let me give you, just from Calculus 1, 2 or 3 examples to make this clear. Limit x goes to 0 for 1 over x does not exist. Because left and right limits, one goes to negative infinity, one goes to positive infinity. Limit x goes to 0 of 1 over x squared, the limit is positive infinity because both left and right limit goes to positive infinity. And finally, limit of sine x over x as x goes to 0 is 1. So here are the 3 cases in which all of the denominators are 0. Example 1, example 2, and example 3, they all have 0 as the denominator. Are they all does not exist? No, right? So you are going to have the same deal with boundary point thing. You have to factor, you have to rationalize, you have to use algebra. Sometimes, yes, you are going to end up with does not exist. Sometimes with infinity, sometimes with number like we just did, 4. So that's the boundary limit problems. And the last type of limits is when limit does not exist, which is where we are going to use the concept of if you approach from one end and you approach from another end, right, the limit values are different. Now, beautiful thing about 3D is that we can do all of those experiments right here and see it, right? So, well, I have this. I just need something boxy to put over here. What's the box? Oh, yes. There we go. Look at it. Observe a point over here. Oh, you guys can't, but there's a point. Well, let's do this point here, right? Fine. So everyone can see this point here. I want to find the limit of this point. Now remember, we are in 3D space now. What is the answer? Answer is just simply a z value, right? Now, this point here, actually limit does not exist. Why? Because the path of the ant walking this way towards the point is going to give you that the answer is 6 inches, or whatever this is. So, answer is whatever. The ant walking on the desk, approaching the same point in space, is going to give answer of 0. So now, this ant over here is debating this one, and clearly, they're both right. And that's why limit doesn't exist. Because the z value for this ant is 0, and the z value for this ant is 9 or 10, whatever the height is. We had the same thing in Calculus 1 when those two lines didn't line up to be at the same height. So now, what we want to make sure is that if we are able to find a path that gives us different value, then at that point limit doesn't exist. You see, if I smooth out the surface, I can approach this, like there's a whole plane on this side. I can approach this one in parabolic fashion. I can approach it as a sine, right? I can approach it in many ways. And I can approach it in many ways on the bottom as well. But if I'm able to find a function that will give me a different value, well then, limit does not exist. All right. You're welcome. No, he's happy I didn't break it. You're welcome. So, what we are going to do now is we are going to do this approach where I'm going to have, limit does not exist, right? So I'm going to take a look at the boundary limit, which means 0 in denominator and all of that stuff. And we are going to get, when we check the paths, right, it's not going to work. So, limit as x and y go to 0 of x plus y squared divided by x squared plus y squared. So, plug numbers in, right? That's the first thing. You see the limit, you just want to plug in and be done. But unfortunately, we get 0 over 0. And we know that because I have this line up there even for Calc 1, you know that can end up anywhere. So what should I do? Well, I can pick a path of approach. And as soon as I pick the path of approach, I'm going to reduce the limit from this 2 variable into a single variable limit, which is technically Calc 1. So pick path y equals x. Guys, simply what I'm saying is I am going to draw the line through 0, 0, because that's what I'm approaching. But instead of having all this infinity of possible approaches, which include then sine, it doesn't include cosine. It doesn't include cosine because cosine doesn't go through 0, 0. But it does include sine. It doesn't include e to the x because e to the x passes above, right? It doesn't include ln x. But it does include this one, it does include parabola, it includes the square root, right? So there are many functions that you can come up with that will go through 0, 0. And then I'm going to approach, as you can see, right? Red and blue approach now. Because what I did is I went from being able to walk anywhere in the xy plane to now being forced to walk on the line y equal x. And I'm going to do the limit this way. So what I did is I figured this out, and now I'm using this. Now this is like a substitution, guys. Just go and substitute in your limit. So now limit, and I just have x goes to 0 now. I don't need y's anymore. And then all y's will be replaced by x's, so I have x plus x, everything squared, divided by x squared plus x squared. Because y equals x, right? So every y was replaced by x. We have a Calc1 limit, so just do it, as Nike would say. You have 4x squared on the top, 2x squared on the bottom, x squares die, and the limit is 2. All right, that's fair. Limit is 2. Pick a different path. Now, you picking a different path means you can now, let's say, approach y equals 2x. You can pick anything. Go ahead, pick sine x right away. Doesn't matter. So pick a different path. Y equals 2x. Now, plug that in. So we have, again, limit x goes to 0. On top, we have x plus 2x squared divided by x squared plus 2x squared. Now, limit x goes to 0. On the top, I have 3x squared is 9x squared. On the bottom, I have 5x squared. 9 over 5. Is 9 over 5 the same as 2? No. Right? So now I will say 2 is not the same as 9 over 5. Therefore, limit does not exist. It breaks that theorem, which says no matter which way you approach to the point, you must have the same value. We got different values. Yes?
Is there ever going to be an occasion where two paths have the same value, but for example, a third path?
Oh, yes.
So how do you know when a limit exists versus, I mean, it's easy to tell when it doesn't exist, but how can you guarantee it does exist? You can't.
Yeah, you actually have to do the proof, which is part of the analysis, which is the part of the, the next level, advanced Calc3, intro to analysis. There are many names, baby analysis, whatever it's called. Different schools call it different thing. My course that I took was a friendly introduction to analysis. All right.
Friendly.
Yeah.
Okay.
Title of the book too. So when you consider this, we are actually going to run into a problem where you are going to run y equal x, y equal 2x, y equal 3x, y equal 4x, and they all keep giving you 2, 2, 2, 2, 2. And then you run y equal x squared and it gives you something else. Right? So to battle this better, we are not going to start calculating y equal x and then y equal 2x. You are going to do substitution y equal mx. Because if you have substitution y equal mx, that takes care of all paths for all possible lines that are going through the origin. Right? And if you do that, then your answer, if there is no limit, will be in terms of m, and if there is limit, then all m's cancel. But then you have to check x squares and x cubes and the square root of x and sine x and all the other functions. So the trick is that you tried all x single x. We'll do another example. You tried all x values, didn't work out. It gave you that the limit exists, right? Then you tried x squared values, again, mx squared, and that also gave you the same value. And then you tried x cubed, and that gave you the same value. What it means is that that particular problem works for every polynomial, pretty much, no matter what you put. But then you switch it around and you say, okay, let me try to plug in, because it goes through 0, 0, e to the x minus 1. E to the x minus 1 is taking e to the x function and shifts it down by 1 unit. That's going to go through 0, 0. Is that one going to give you the same number? If it does, well, you might have hit the lottery then, right? Limit probably exists, and it's the number that you're constantly getting. But if you try all the polynomials and you're trying transcendental functions and they're still giving you the same number, that might be the limit. But the chance is that pretty much going from linear to quadratic, it's going to immediately explode, right? So let's take a look at another example and then talk about continuity, which is the second part of this lecture. I just want to get into the homework and pick one of these problems for a multiple path. So let me write over here, use y equal mx to check all linear paths. Also, I mean, this is new to you, so pay attention. Make sure that when you are working on these functions, make sure that the approach actually goes through the point, all right? I mean, imagine me trying to figure out if the limit, right, over there by the door is 3, and I'm walking in this area over here, right? So that's why I said that e to the x minus 1. It brings it down to go through 0, 0. You can't use anything. Aha. Let's see something spicy. Or not. I don't know. Pick something 27 through 32.
29.
29. He knows what he wants. Leave him alone.
Is it a good one?
Quality one, nice.
Spicy.
I know. I kind of wanted to pick this one, but then I didn't. And then now you made it. Y to the 4 minus 2x squared divided by y to the 4 plus x squared. As it always goes, step number 0 is plug in. Plug in 0, 0, and if you get 0 in denominator, then we have to explore other things. We are getting 0 in denominator, right? So we have to explore other options. Now, the next part is you ask yourself the next question. Can I factor? If you can factor and cancel and then plug in and get 4, like we did, you're done, right? Well, can't factor and can't cancel, right? Y to the 4 plus x squared doesn't factor over real numbers, right? Because you would have to have I. It will be x squared, right? That's, I mean, y squared minus or plus xi. So that doesn't work. Great. No roots, can't rationalize, do any of that stuff. So yeah, this pretty much is set up for limit does not exist. So that was a process of elimination, thinking out loud to see where could we possibly get to this. Now I'm going to start checking the paths. Instead of checking y equals x, I'm going to check y equal mx to check all of the linear paths in one. Someone just peeked in the classroom before and walked away before I got the chance to go, come on in, it's Calc 3. Anyway. So pick a path pick a path, and no, pick the path. No, pick paths. Y equal mx. All right. I have infinitely many approaches in here. Right? 1/2 x is in there, and 3/4 half x is in there, and 3x, and all of that. Plug in. So now limit x goes to 0. Is y to the 4th is now going to be mx everything to the 4th minus 2x squared stays as is, and then mx to the 4th plus x squared. Now we are going to solve this limit. We can first apply the 4th power. Don't forget to write limit in every step. Triggers my allergies. To you. All right, and plus x squared. There we go. So now what we are going to do is we are going to factor out, right? The only thing I can do is factor out x squared, and then those are going to cancel. So they cancel. And now observe what happens as I... So now we plug in x equals to 0, and we are going to get -2. Do we all see that? As x goes to 0, that kills these m's, and you have -2 divided by +1, which is -2. We just proved that all of the linear paths into the origin will all give -2 as the answer. Now, we say, all right, we just tried infinitely many approaches, and they all lead to -2. Right? Tempting to say limit is -2. But, you know, let's check more. How about we check y equals mx squared and see if that is going to change the landscape. So limit x goes to 0. I have mx squared to the 4th minus 2x squared divided by mx squared. I was saving this for the test. God damn it. Plus x squared. I gotta ruin it here. He picked it. So now, as I square everything, the only thing again that I will be able to kick out is x squared, right, on top and the bottom. Now what's left on top? We have m to the 4th, x to the 6th, because 2 times 4 is 8, and I took 2 out, so 6 is left, minus 2. And on the bottom I have m to the 4th, again 8 minus 2 is 6, so x to the 6 plus 1. As x goes to 0, what do we get? We get -2 again. We tried infinitely many polynomials, right? Of the first order and the second order, they're all screaming -2. All right, well. Let's check y equals e to the x minus 1. That's going to go through 0, 0 as well. Is this going to help? So now I have, where's the problem? So it's x to the 4. So It's e to the x minus 1 to the fourth minus 2x squared divided by e to the x minus 1 to the fourth plus x squared. Oh, I can't factor anymore. But I can plug values in, right? What happens when you plug in x equals 0 now? I get 0 in denominator. Good. Do what? No, it's e to the 0 is 1. 1 minus 1 is 0, right? So we can do that. So what do I do next? What can I do with this? You know, I'm done, right? It's like, yeah, that's it. Like we tried twice, and that's. If anything, you remember that problem when we stayed for 45 minutes. So reminds me, you should put that on a test, right? What now? We have all of the Calculus 1 might at our disposal.
Oh wait, so once you...
Yeah, we can. This is now Calc 1 realm. So we can do L'Hopital on this one and see what we get, right? This is 0 over 0, so we can use L'Hopital's rule to see what's going on. So by L'Hopital's rule, it's actually Bernoulli's rule, but such is life. We have 4 e to the x minus 1 cubed times the derivative of the inside, which is e to the x, minus 4x, divided by 4 e to the x minus 1 cubed times the derivative of the inside, which is e to the x, plus 2x. This is still 0 over 0 because of the e term, right?
Again.
Do it again. Welcome to Calc 1. So now we have, well, now we have the product rule, right? So this derivative is going to be very lengthy.
Where's the negative drop of
No, you draw the line. And I mean, there is a way to bypass product rule if you want to, because you can stuff this e to the x inside, which we could do. It's going to become cube root of e to the x if it goes in, right? And when you cube it out, it's going to... I'm sorry? Which path would you like to choose? You want like square root of x?
Yeah. We're just going to stop?
But
no, we can't stop.
But the square root of x is not going to... square root of x doesn't go into the negative. Is it going to... wait, square root of x is going to give us... Let me see. Square root of x is going to be x squared. That should work, right? Square root of x... x squared minus... That's fine, we'll do this. 2x squared. And then x squared plus... Yeah. That can... Yeah. Square root of x. Good. This should work too, because when you take the derivatives now, right, the part... Oh no, this is the term that gives you 0. Yeah, you see? Yeah, but see, as you take the derivative one more time, these terms that used to survive and give you negative 2 will be gone, right?
No, but it will... No.
Yes.
Negative 4 over 2.
Yeah, and then you take the L'Hopital again?
No. No, but don't you not have to take the L'Hopital
because that would be 0.
So we would get, hold on, we would get a mess minus 4, and then a mess plus
and
2.
Mess equals 0.
Mess equals 0.
Yeah.
So it's negative 4 over 2.
So can we just do that? Like,
Negative 2. Great.
honestly, though?
Path y equal root x. Or you will have to.
Awesome.
You will have to.
Can we write mess
I'm gonna do it.
and trust that it equals 0?
Yeah, I should.
Is it? Is it? So path, let's see this one. So now limit x goes to 0. We have a square root there, so that's going to be x squared minus 2x squared divided by x squared plus x squared. So this is now limit x goes to 0 of this is negative x squared divided by 2x squared. Now we get negative 1/2. So we had,
Negative 1/2?
yep, we had negative 2, we had negative 2, negative 2, and now we have negative 1/2. Limit does not exist.
Are you?
So is there like
I'm
a
not
limit
gonna
to
do
like the functions you want us to check?
I'm
At
sorry?
least you're honest.
Is there like a limit to the functions you want us to check? Like,
Yes, yes. Generally, most of the problems will be done as soon as you try this, because if it gives you something that depends on m, that means picking m changes the limit, right? So when you solve, let's say you solve the calculus 1 limit, and you end up with m plus 1 over m. If this is the answer, then remember, if I pick y equal x, in that case m is 1, your limit in this case would be 2. If I pick 2x, then m is 2, it's 3/2. And that's different than the previous one. So as soon as you get the limit to depend on m, changing m's obviously create that. Also, you're trying mx squared. We just seen the square root of x is good one. And then generally e to the x also can kill these pretty much. E to the x, but I have to say minus 1 because it has to be shifted down. And that would be the bank of things to try. But then there's, sine and sine x and so on.
How many of these, like, are you going to expect this to actually, like 5, 4, 2, 1?
Problems? I'll make special exam just for you.
Like tests, like, are you... She means how many paths do you expect us to test?
Well, you have to test whatever is... What is that?
What?
Break? Well, this calls for break. Are you sure you're going to leave? You just got here. He's confused. He's like, yeah, I'm leaving. Anyway.
Why is that?
Ask Brian. I'm not sure.
I'm hungry and want to say probably
So yeah, that's that. The next part of the lecture is continuity, which is going to be exactly the same as Calculus 1. We are going to write the same definition, except it's going to be for Calculus 3. And then we have two theorems that follow. Continuity. So where do we start? We start with the continuity at the point. Following three things have to be satisfied. F of AB exists. Maybe I should say continuity at the point AB. There we go. So function needs to exist at that point. 2. Limit of f of xy needs to exist as xy goes to AB. And 3, 1 has to equal to 2, which means limit of f of x needs to be equal to limit of f of AB. Limit of f of x y, there we go, as xy goes to AB. So this is what we have. Now I am going to state that function, though this is the next theorem, since this is continuity at a single point, if you want to see if the surface is continuous, guys, observe that the surface of this desk is not continuous. Look.
Try it again.
There we go. So the surface of this desk is not continuous at this line here because there is a nosedive, right, 90 degree down. Limit doesn't exist at this edge. Remember, my path approach that is this way is going to give me whatever amount of height is this and 0 if I approach from the other side. This is not continuous surface. Now, consider two desks that are adjacent to each other. They are continuous, right? The surface is continuous. Yeah, I know there's a little line there, but yeah, you are sliding that can. Perfect example. Thank you. So as you're sliding the can left and right, you see that there is continuity between the two surfaces. Limit exists, the function value exists, which means there is no gap that the can fall into, and they are the same value. Now, it fails at the desk here because limit doesn't exist. Function value exists. You can define it to be this one. And so number 1 is okay. Number 2 is the one that fails. Now, once we define continuity at a single point, we can say that the function is globally continuous if it's continuous at each point of its domain. So now, theorem would say function f of xy is globally continuous if it is continuous at every point of its domain. And one more definition, theorem. So this is a theorem, and this is another theorem over here. If you have multiple continuous functions, their combinations and compositions are also continuous. So if f of xy and g of xy are continuous on the domain. Now it has to be combined domain, right? Then we write f plus g, f minus g, f times g, f divided by g provided g is not 0, f squared, or I put f to the n, and f composed with g, right? So you plug in one into another, are all continuous. So if I put continuity problem on exam, you have to solve it by writing a paragraph, right? I have, let's say, sine of xy plus y cubed continuous. Right, that's the question. You answer this by writing a paragraph. You will say that both, since x and y are independent input variables, that's just right. They're not functions. X and y. See, y is not a function. You have to start thinking about it. Y is just as x. It's an input variable. So now I have that sine x is continuous, right? We know that from Calc 1. And function composition is continuous. Therefore, sine xy is continuous. Y cubed is polynomial. It will be z equals y cubed. That's a polynomial. Therefore, continuous. Again, theorem in Calc 1. So now, finally, we know that f plus g is continuous by the theorem above. Therefore, sine of x y plus y cubed is continuous on R2. The domain is in R2, right? It's two-dimensional domain. So it's paragraphs. We write paragraphs now, and you have to get all these ducks in a row. Right. That's it. I hope you're not disappointed. Continuity, you will be writing paragraphs, and for limits, you will be calculating stuff. All right, so that's that. We'll resume with 12.4, I guess.